Hi, I'm Mark with Macroscopic Solutions. What I want to now sort of show everybody is now that the system has been built, we're going to get into the functions of the system. I just want to show how the controller is going to be programmed. Now, here it's very important to understand field of view on the Macropod MacroBox system. The reason for that is that the field of view is going to be the exact number that you use in order to move the camera along its y-axis and along its z-axis in order to form an overlap to generate a total combined panoramic image. So I have the MP65 1 to 5x written out here, the 100mm lens. We're not defined by magnification, but here we're defined by a working distance. So that is, this 15 centimeters here is denoted by the front of the lens down to where the focal plane is contacting your sample. If that distance is 15 centimeters, that's the number that we're interested in. That's why everybody's kit is provided with an actual measuring tape. So what is field of view? Field of view is the total amount of area that the camera is seeing. Therefore, if this is my entire insect tray, my insect box, or if this is my entire soil box, basically the camera might only see that much of the total area. Remember, we're focus stacking and we're producing a panoramic to produce a very high quality image. So let's just say that this field of view corresponds to the magnification at 1x. Now this number I'm going to be speaking out arbitrarily. However, let's say that the 1x is 2.5 millimeters by 5 millimeters. So that means that our long axis is going to be 5 millimeters and our height of the field of view is going to be 2.5 millimeters. We can't just program that into the amount of translation in the system, because there will never be informational overlap for the software to generate and merge two images. We need a 20% buffer in order for us to actually collect information along the boundaries in order to generate a panoramic, right? If you're taking a panoramic with your phone, you can't just take a picture and then take a picture of there and hope they come together. You need some bit of information in between them. So in order to do that, what we're going to do is we're going to take our 5 millimeters, we're going to take our 2.5 millimeters, and we're going to multiply them by 0.8, which is going to give us a 20% overlap value. So at 5, that leaves us with 4 millimeters. That means we are now going to be programming our controller so that this long axis moves 4, and this axis will move 2 millimeters. However, we're not quite done yet. The stack shot itself that holds the camera, it will move at exactly the number that you program. So the focal plane, which is actually another value that we give in the table, depends on the aperture. So if the aperture is closed at f12, the focal plane is really small, so you're maybe looking at 0.5 millimeter. But if it's open and basically like f2, I'm sorry, it's the other way around, it's going to be even smaller. So basically now you're looking at basically a focal plane that's on the orders of microns. So you need to keep that in mind, but again, we're kind of touching on this now so you'll kind of see how this all works. Sorry, that was confusing, kind of forget that last bit. We'll stick with what we were talking about, we'll get to depth of field in a moment. Okay, so remember, this is what we're talking about as field of view. What sidetracked me is that basically the rail systems, which are different than the stack shot sliders, which only move a total distance of either 10 or 20 centimeters, sliders are obviously moving a full meter. And they move at a different rate. So that rate needs to be understood in order for us to modify these lengths. Now, that rate happens to be exactly 14.52 times faster than the actual stack shot. So you need to take these numbers and you need to divide them by 14.52, each of them. And that answer is going to be the number that you program. Now remember, your long axis, based on the field of view in the camera, that's this here. Even though to us, that would be considered your x-axis and this would be your y-axis. In this case, we're using the x-axis for focus stacking. So remember that this is actually your y-axis and the short axis is actually your z-axis. Your x-axis is going to be the depth or the total depth of the field. Okay, so not to confuse you, this is your y-axis, and this is your z-axis. I know that does confuse you. Anyways, the answer's here, so 4 divided by 14.52. Let's go ahead and we'll do that right now. Well, 2 divided by 14.52 is 0.1377. And 4, obviously, divided by 14.2 is just going to be double that to 0.2755. 0.2755. Now, these are the actual numbers that you would program in the stack shot to set up the y and the z axis. That's if you were doing your own calculations. But I'm just showing you how we arrived at these numbers in the table that we provided for you. So these numbers are already figured out. So we're just sort of giving an example of the 1x. But just know that the 1x obviously is going to have a larger field of view because it's at 1x magnification, whereas the 2x is going to have essentially half that field of view because we're at 2x magnification, and so on down the line. So the amount of area that you see in each magnification is going to get progressively smaller. So these axes are going to change. But again, these numbers are already calculated out for you in the table. But again, just for your understanding, the formula for these, so either the y or the z axis, is going to be either your length or your height times 0.8 divided by 14.52. So that's the formula that you would have in order to set up your y and your z axes. Now your x-axis is denoted by your depth of field. That's the, basically looking down at this insect tray, that's the part that's coming up at you. So let's just sort of think three-dimensionally here. There's our box, and we basically need the height of the box in order to photograph the material in it. If you're just looking at the surface material, you don't need the full height of the box, but you do need to know this. Now that height, depending on your magnification, is going to change, and depending on your distance away from the sample is going to change. But that height is basically corresponding to your aperture. Your aperture is going to drive this. So, if you have an aperture, for example, f11 versus an aperture of f4, f4, your focal plane, so the depth is going to be really shallow, whereas f11, your depth of field is going to be pretty deep. However, you start to compromise lighting, and you start to compromise quality at f11, whereas you don't so much at f4, you just have a very narrow depth of field, so the time it takes to capture images is significantly greater. So this might be 1 millimeter, this might be 6 millimeters. And what's really nice for the stacking portion of this is that this is actually tied to the exact distance. So you can basically multiply 1 or 6 times 0.8. Remember, you need your 20% overlap. And you can arrive at 0.8 millimeters here. And at 6, so, yep, roughly it's going to be something like 4.4. I don't know if that's actually what it is. My brain is not thinking right now, but basically we're taking the depth of field, multiplying it by 0.8, and we're arriving at an overlap. You don't need to divide these numbers by 14.52 because these are not on a rail system. So this is the number you can actually enter for your x-axis. Okay, the last sort of thing to review is your MP65 works by magnification. Your 100 millimeter does not work by magnification. It works by distance from your sample. So 15 centimeters away from your sample, you're going to be much, much closer. 30 centimeters away from your sample, you're going to be much further away, so you're going to get a lot more field of view into each image. So at 15, you might only be seeing a small part. At 30 centimeters away, you might be seeing a very large part. So your numbers are going to fundamentally change. So it's just very important that you measure the distance. So if this is, if this is your camera and this is your lens, and you're looking out towards the box, you just want to measure the distance from the front of that lens down to where you're imaging. And you want to do that in 10, 15, 20, 25, so on. So 5 centimeter intervals, And as long as you pick one of these 5 centimeter intervals, then you can always refer to that table that you've been provided to find your x, y, and z values. It's been a while since I've taught. It's been 10 years since I was a graduate TA, so I apologize if this is a little confusing. It's not exactly altogether necessary. However, I did just want to present this information for you in case you do want to sort of extend your understanding of how we arrived at those values within the table and how you would go about calculating your x, y, and your z axes. Hopefully, as you start using the system, this is going to become more intuitive. You're going to understand how we arrive at these values. The most important part, obviously, is that when you're working with the longer rails, is just remembering that those rails move at a rate that's 14.52 times faster than the stack shock motor rails. So again, I'm Mark Smith with Macroscopic Solutions. Thank you for watching this video, and in a moment we're going to apply these values in a real setting and turn the system on and show you how to use it.